Okay. So the first question is, what's an LLM? Effectively, LLM, you can think of it as a black box. You have some input, you give it some input, some prompt, some text, for example, and then the LLM will just give you some output, effectively serving your what you ask for it. So the LLMs are not deterministic. So for the same question, there is a different probability of getting a different answer every time you ask it, and so on. But you can use it for many tasks. You can use it for either conversing, providing some translation, Q&A, classify some text, providing some summaries, transcribing videos, text generation, and so on and so on. The idea is that there are various popular LLM models there, some foundational models. So for example, I'm pretty sure you all know ChatGPT, Gemini, Claude, Mistral, and so on. So they have different characteristics. So they have different sizes. For example, ChatGPT-4 was estimated to be roughly 1 or 2 trillion parameters, between 1 and 2 trillion parameters. Gemini in the order of 120 billion parameters, Claude into 200, and so on. And each one, if you happen to use all of them, you can see that they have different strengths and weaknesses. So, and some they can provide some multimodal and code capabilities better than others, for example. Some others they can provide some better reasoning, and so on. The first three in this table are effectively, okay, sorry. The first three are, these are owned by, these are proprietary to OpenAI, to Google, to Anthropic, and so on. The other three, the difference is that they are open source. Okay, so actually you can take the weights and you can use them from wherever you want. And these are usually used for fine-tuning third-party models and so on, right? And then we also have some specialized LLM models. For example, we have one called EuroLLM. This is in the size of 9 billion parameters. This was trained from scratch by the European Union. And the goal of that is to provide multilingual EU languages and translation. We also have Cricri and Meltemi. These are fine-tuned versions of Llama 3.1 and Mistral. And they are towards providing, these are Greek LLMs, for example, that you can use and converse in Greek and so on. Then you have CaSToRC. This is a fine-tuned version of Mistral 22 billion parameters. So this is an LLM that is specialized in code generation, for example. And then you have MedGemma. This is a fine-tuned version of Gemma 3. And the idea of that one is to provide some specialized knowledge in the medical domain and so on. So we have the foundational models. These are very good in general tasks and so on. And then you can also have some specialized LLM models that were either fine-tuned or created from scratch. Now, the first session is about local LLM deployment. And the question is it even hard? I mean, don't you just use the OpenAI API if you have used it in the past? And, well, sort of. Yes, but no. Okay. The idea is that you have this abstraction. You have the user, you send your request, then you ping some server, let's say the OpenAI server, and then you get the response back. Conceptually, that's just it. But in doing so, there are some intricacies that you need to deal with. So, for example, the first question is, what models are you going to use, right? So you have mainly hosted APIs that they have mainly proprietary models, and then you can have self-hosted APIs that you have open source models and so on. And this varies in where they are deployed. For example, the hosted APIs are usually by some third-party provider. So you have OpenAI, you have Anthropic, Databricks, and so on. And then you can have the self-hosted open source LLMs, for example, that are hosted on Hugging Face, or you can get other models as well and host them on your own machines. But why would you want to self-host yourself? And the answer to that is that there are many reasons. So in the long run, you provide, as you use more and more the models, the costs are sort of plateau at some point on the equipment cost and the maintenance cost. Although if you're using OpenAI, for example, the costs are always scale with the usage. And you can get better performance actually, depending on the task. You can use fine-tuned models, for example, if your task is, if you want to use code generation and so on, right? And then you have the privacy and security issues as well, because if you host the local LLM, if you host the LLM locally, then you don't provide any data to a third party and so on. And many enterprises, they care about open source for many reasons. The main ones are the cost, the customizability, you have the flexibility to select your own LLM and so on, and control. So it makes sense if your concern is security to self-host, but the question is how much really harder is than using the OpenAI API. And the answer is it's much harder actually, because you have to deal with a few things that are not very straightforward. Models are large, and the size of models is still increasing, and so on. On the other side, GPU prices are super expensive. If you want to buy one H200, you be prepared to pay 30 to 35,000 euros. Okay, just for one GPU. And the field is still evolving, and is evolving quite fast, right? And these are the three main reasons that, the three main issues that you have to deal when you want to host centrally and locally. But there are actually some tips on how you can make this deployment less painful. For example, you need to know your deployment boundaries. So first, you need to know the latency requirements, how much time you want to wait from the time you send the prompt until you get the response, for example. How many users are expected to use the system, either asynchronously or at the same time, and what hardware you have available to you. Do you have any GPUs at all? Do you have powerful GPUs? Do you have one GPU, 4 GPUs, 100 GPUs? And this one, these three requirements change your boundaries quite a lot. The other thing is that you should always quantize your models. So instead of using all 16 bits or all 32 bits, let's say, for the model weights, you can use 16, 8, 4, or even 4 bits for each weight. And this actually increases the performance of the model without sacrificing a lot of the accuracy. And the main idea is that you should start with the available infrastructure and then work backwards. So if you have, let's say, one GPU card that has 40 gigabytes of available memory, then your limitation is on which models you can use. So for example, you can use the Llama 13 billion parameters that is around 26 gigabytes of RAM, or you can use a Mixtral 4 bits, that's 22 gigabytes, but you cannot use a Mixtral that's 19 gigabytes, right? Then you also need to think about optimizing inference. So how you can batch the many requests together. You need some sort of strategy. Your strategy might be that you have no batching at all, and then you process the requests as they come in. This will give you some steady utilization of the GPU, but you won't be able to fully utilize the full power of the GPU. You can also have dynamic batching, so you can wait between the different requests and process them in groups. For example, you can do some batch requests. You can process requests every 1 hour, for example. So this is good for tasks that you don't really care when you get the answer, unless as long as you get an answer and so on. And then continuous batching is sort of something in the middle that will sort of keep the utilization of the GPU steady, but and towards the 100%, but there's some more complexities in dealing with that. Okay. The other thing that you need to decide on is on parallelism. So assuming that you have many GPUs, how are you going to use them? The first approach might be no parallelism at all. If I have 3 GPUs, I can launch 3 different models on each GPU, for example. But in doing so, if you have larger models, for example, like Llama 3, the 70 billion parameters, you might not be able to run it on a single GPU if that has, let's say, 40 gigabytes of RAM only. So if your model is 60 gigabytes, you cannot use it at all, right? The other strategy is to use some sort of pipeline parallelism. So you split the model layer by layer across GPUs, but the idea here is that only one GPU is active at each time step, right, until you finish the execution. And the other approach is using tensor parallelism. Effectively, you can split your model into several chunks. Each GPU gets a different shard and is processed separately. And the idea is that you can now utilize the GPUs at the same time, and then you can split the model, let's say, from 60 gigabytes into 30 gigabytes and 30 gigabytes, and you can process it on multiple GPUs and so on, faster and without wasting any GPU time. So this is, again, there is no right solution to that, but there is something that you need to keep in mind when you do your local deployment. And the other idea is consolidating infrastructure. So you have a central compute infrastructure, and you'll see today also in the hands-on that you can have the models deployed in some central infrastructure, and then you can build applications on top of that models by pinging the model, right? So you deploy once, and then you just maintain that. And the rest of the organization uses the models as a resource, and they can build on top of that. And this effectively increases GPU utilization. So you have this idea of the inference service. So instead of having, let's say, if you have, let's say, access to 4 GPUs, instead of launching one model on each GPU, you have some sort of inference server. You have the model central, and then the resources are all used by this inference server, and the server will decide what's given to each application, for example. So there are 2 aspects. So you sort of decouple the infrastructure from the application, and different people are responsible for different things. So as a developer, you won't be really care about the infrastructure, but you'll be only using it as a resource. And something else that you need to have in mind, and this is, I think, ambitious as well. So build as if you're going to replace the model within 12 months. And I think 12 months is quite a lot. The landscape is sort of evolving quite rapidly. So even if you have one model that seems to perform best, let's say, if you're going to build your infrastructure around that model, then in 12 months, you'll have problem, because you'll need to change the model into the new fancy thing that works better than the previous one, and so on. And the idea here is that you should have abstractions and focus on building AI applications and not how the models will evolve, right? So your infrastructure it won't be dictated by the latest model that you have today, but you should allow some room for in case the model changes into something larger and so on. And then you can also use small models. So we're talking about large language models, but you can also have lightweight versions of these traditional models. And these are designed to operate efficiently on resource-constrained environments, right? So either smartphones, embedded systems, and so on. And these are much smaller than the typical foundational models and so on. And the idea is that they still retain their core natural language processing capabilities. So you can still use them for text generation, summarization, translation, Q&A, and so on. And there are many methods of doing that. So three that worth mentioning is through knowledge distillation. So you have a teacher model, the foundation model, and then you have the student model, and some knowledge is transferred from the teacher to the student. You have pruning. So if you have different weights and less important parameters in your network architecture, you just sort of remove these. And then you have quantization. We already mentioned that. So instead of using high precision numerical values, you sort of convert them into lower precision, even to integers. And the benefits is that you have low compute requirements, and that translates into faster inference. You can use it on device. You have cheaper deployments. You have still the customizability and low energy consumption, and that means low electricity bill. And you can see that you have similar. So you have the Gemma 3, 4 billion. So this is a small model from the actual Gemma. You have Gwen, you have Llama 3.21 billion parameter. This is a smaller version of Llama. You have DeepSeek and so on. And then the applications are pretty much the same as the ones that you use the large language models. And the idea about that is you can sort of try it and experiment with small language models, and if they meet the requirements of your task, then it makes a lot of sense to use those instead of using a large language model that will require significant more resources. Okay. And just to summarize here, we have, if you're doing the LLM deployment, you need to figure out your deployment boundaries and then work backwards. So what sort of hardware you have available and work backwards. You should always quantize. Spend some time thinking about how you can optimize inference, either through the batching strategies or the parallelism strategies. Then you should also consolidate your infrastructure and launch the models there and provide them as a resource. Build as if you're going to replace your models within 12 months, I would say 6. And use small models when you can. Now, how you can choose the right model, that's a compromise. That's a sort of trade-off between size and performance. Usually, if you have small models, you have faster inference. And if you have larger models, you have better accuracy. So you need to find the sweet spot between those two. Now, also the task stability. What do you want to use the model for? If you want to use it for code generation, then it might make sense to find a model that is good on code generation, even though if it might not make great summaries, for example. Okay. And then licensing and costs. So if these are open source or if you can use any commercial options and so on. Now, you can find many open source models from the Hugging Face ecosystem. So you can go to the webpage. If I'm pretty sure many of you already did that, but you can go there and you can find the different models. You can open the model card and you can sort of read the information about the model. You can see its size and so on. And then the idea here is that you can use those models and deploy them locally. So you have two main options that you can use for local deployment. You can use VLLM. We're going to be using it today on the final hands-on, and then Ollama. And at least to myself, the distinction on when to use each, I think it's very clear for me at least. So if you're going to deploy the LLMs on your local laptop, for example, or your desktop, I think it might be better to use Ollama, right? It's easier to use, and VLLM, you can use it for if you want to run LLMs very efficiently. So it's much more efficient compared to Ollama, especially when you try to serve multiple users in one go. So there are four main pillars that you can think of about when you want to do the local deployment: the concurrency. So VLLM usually handles multiple requests and staying steady, even with a lot of requests as they come in. We're gonna figure it out. We're gonna find out today if this is true, if you're using it multiple users at the same time. Now, speed also. So for example, just to compare, a VLLM for 16 requests in one go, it took only about 9 seconds per request. Although Llama at the same time, for the same amount of requests, it took 17 seconds. And then for 16 concurrent requests, the VLLM also produced almost 2 times as many tokens per second as Llama. And even when we tried until 32 requests, it sort of produced 100 tokens per second quite smoothly, although Llama started to struggle at this time. Okay, and just as a rule of thumb, you can use VLLM if multiple users are going to use these models, or Llama if you're going to use it for some personal projects and so on. Now, to start with VLLM, so first you probably need a GPU. And then first you can install it through pip, right? And then what you can do is you can start serving the model. So for example, here you can serve the model with VLLM serve, and then you select the model. And this will effectively download the model, and it will sort of make it accessible at the local URL through the port 8000. You can also change that through some different command line arguments. But the idea is you install VLLM, then you do VLLM serve, and this will sort of launch your model locally. And if you happen to use the OpenAI the OpenAI API. So this code is the same as if you were to use the OpenAI API. And what you need to change, so see, we're still using from OpenAI, import OpenAI and so on. We still use the same client, but what we change is the API key, which is going to be our actual API key, and the base URL that now points to the local instance of the model that we deployed. So the remaining of the code stays the same, okay? Also, you can have different tools for interface. You can have OpenWebUI, the Hugging Chat, anything LLM, and so on. And this is effectively the front that you'll see as a user when you try to use these local deployments. This one shows the OpenWebUI. We've also played with that ourselves, and we found it quite useful. And users are also familiar with this type of environment as well. You can also use other environments, like other fronts, such as Streamlit, for example, is also quite good. And now the economics of LLMs. If you want to do some local deployment of LLMs, you can set different price points and different depending on the capabilities you might want to your infrastructure to have. So the first one, the simplest one that we could sort of build ourselves, is one RTX Pro 6000 Blackwell GPU, 96 gigabytes of RAM. So this is quite decent. And this one effectively starts at 17,000 euros. Well, 18,000, I would say. And the price per GPU here is 8.5K euros. So this is a very good workstation that you can use for your own local deployment. And then you can sort of extend the same workstation, so the same casing, the same motherboard, with 4 NVIDIA RTX Pro 6000 Blackwells. So you'll have total of around 340 gigabytes of RAM overall. And this one now comes to 50,000 euros, right? But this is quite decent. And you can also have something similar as a system node, for example. You can have eight NVIDIA GPUs. In this case, we have Adam, but you can sort of upgrade them to the newest Blackwells as well. They only differ by 1,000 euros. And now you can have a whole server with 8 GPUs. In theory, you can use either 8 different models at the same time, or you can serve one larger model for multiple users. And this now comes to the 85,000. And now you can also scale it further if you start using the bleeding edge GPUs such as H200 or B200 and so on. Okay, I think that one goes all the way to 300,000 euros. But those ones are much better if you want to do fine tuning, right? If you don't want to do any fine tuning, I think around this around these prices, you are good to go. And the main difference between the system on the left and the system on the right is that the right one, you can duplicate it and scale it with high-speed interconnects. So you can have, let's say, if you want more even more GPUs, you can have the same exactly replica of the node n times, and you now have n times 8 GPUs. Okay. Now, the second session is about a quick introduction to racks. I will just mention a few things, and then they will become more clearer in the next sessions that are only about racks. And the idea is that if you want to influence the responses from the LLMs, there are different approaches to do that. But as you select a different approach, the complexity, the cost, and quality change. So first, you can try with different prompts. You can do better prompting, and then you can try to sort of make the model respond to what you need. This is easier to do. And then you can sort of move into racks. You can sort of provide extra information to the model through some database. And effectively, you need to spend some time, you increase the complexity and so on. And then you can sort of fine-tune the models as well. So you can perform a few iterations of training so that the models will be updated with your own data. And this is you're increasing complexity and cost as well. Or you can train from scratch, right? The first few you can do it on your laptop, and the last two you'll need probably a supercomputer to do them. Okay, so these are the different ways you can influence the LLMs. Racks effectively provide you some sort of a process where you sort of so RAG first stands for retrieval augmented generation. They provide you some mechanism in order to provide some external information to the model, but this is sort of an intelligent way of doing that. So as a user, you have some documents, you sort of put them in some database, and then your goal is to retrieve only the relevant ones and include them in the context of the LLM so that it can provide you a better response. And the main reason for using RAGs is to reduce hallucinations. So if the model won't know something, instead of saying you, I don't know, it will probably say something that it's irrelevant, wrong, but it will say it with high confidence. And effectively, this is what's hallucination. So if you ask the model, what's the capital of France, and it doesn't know for whatever reason, and it will probably say that, for example, the capital of France is Marseille, and that's it. So this is an example of a hallucinated response. A more grounded response would be the correct one, which is the Paris. Okay, and if for whatever reason the model doesn't know that, and you have some RAG in place, it will retrieve the information from the database instead of from the trained data that it has. And effectively, RAGs, they split into two phases. So first, you have the indexing phase. So you have the indexing pipeline that you start with the documents, and your goal is to extract the content. feed it into the embedder, and then create some sort of embeddings. So these are, let's say, some vectors, numerical vectors, that then you store into the vector database, right? So that's the first phase. Usually you do it once unless you have new information. Then if you have new information, you can sort of reindex that new information that came in. And how it works effectively, let's say you have the document. You have different phases of the document. You can use a context extractor, and then your goal is to effectively extract the content. So you have some text, some paragraph, you have some table, you have some other paragraph, and so on. And then you want to create from this text, you want to create the vector embeddings. So these are a numerical representation of the same text that you have extracted. So for each piece of text, you want to create these vector embeddings and then store them in the vector database. Okay. Yeah. And the idea is that this vector database will have some different vectors, and you will end up with some vectors stored in the database. And the idea is here that when you want to get a response from the LLM, you provide the user prompt. So now it goes through the embedder again. And the next step is try to retrieve any relevant information from the database that you stored earlier and include this in the context of the LLM so that it will provide the response. And the idea is you have the content and sort of you query through the embedding model. So you end up with some vector embedding. So you end up with some new vector. And then you go through the database and you perform some similarity check with the vector embedding that you just created with the ones stored in the database. And the idea is it will give you the results back, and the results will contain vectors that are similar to the input vector you have created just now. And I think Nikos has a nice example of doing that actually in practice, and let's see how that works. And the idea is so you retrieve the vector now, and you include that in the context of the LLM, and it will provide a more informative response. Okay. So compared to the traditional LLMs, the knowledge in those LLMs is static. So it's what it acquired through training. Okay. Using RAGs now, you can have a more dynamic knowledge base through the vector database. And the traditional LLMs may hallucinate. RAGs are usually more grounded. It doesn't mean they will never hallucinate, but usually they are more grounded. And if you want to perform any updates on the traditional LLMs, then you need to sort of either retrain or perform some fine-tuning. And with RAGs, you just need to update the knowledge base. So you need to rerun the indexing phase that you have at the beginning, and then your database will be updated. And finally, the main reason that you might want to use RAGs, you can have domain-specific knowledge ingested in your LLM that you want to use, for example. Okay, and a very popular use case of LLMs are chatbots. So usually in customer support, you can ask questions about the specific company, for example. You can have it for legal research, going through the available laws and documents. For healthcare is also used. And then enterprise search. So if you want to, let's say, provide a filtering mechanism for the different policies in your company and so on, that's a very good use case of RAGs. And the elements of RAGs, so you have the data that you need to have in place, the documents that you need to index, Then you need to create some sort of database. This is a vector database. You have the interface. The interface can be the Open Web UI front that we've showed earlier. And then you have the server that will effectively run the model. So you need to also have the infrastructure that will run the models that you need for RACs. And there are different databases that you can use. We've experimented a lot with Milvus, but there's also Pinecone, Chroma, and Drand. And then some frameworks that you can use for building your own racks. You can use Llama Index, LangChain, RackFlow. And today we'll be using CaSToRC in the final hands-on section. That was all from me. Thank you for listening. Do you have any questions before we move on with the interesting parts of today? The hands-on. Yes.
Yes, hello.
No.
With time, where to have to basically install global LLM and we type them out. Not so much success. So I have a couple of questions. How easy is to pay? Do we need to pay a local LLM for better responses, basically for code generation? Because we try a few, I would say, small also hardware limitations. We were trying to figure things out. So do we need to fine tune? And if we do, how easy it be?
I think the process of fine tuning, actually the code for fine tuning the models, I think it's simple enough. The process of that, but the rest, I think it's you need to have a lot of data first of all. Well, using the data that you have, first of all, you can perform a few iterations of training. So instead of starting from 0 random weights all the way until you end up with some good weights and some good accuracy, you take the model as is trained already, and then you want to provide some data to perform a few training iterations in order to change the weights towards your data, let's say. I think you can do it with PyTorch and existing libraries as well. But the idea is you will need significant resources, computational resources. Yeah. Because, I mean, if you want to take one, let's say, for GPT-4, if you want to take, let's say, if there was a way to take GPT-4 and try to fine tune it, even just performing one epoch, first of all, you need to feed 2 trillion parameters into one machine. So first you need a lot of GPUs that will handle the capacity. If we're talking about fine tuning, we're talking about even more memory. So maybe times 2, times 3 of the memory that needs a model to run. So you need the infrastructure, but also you need a lot of data for fine tuning. I would say try and figure out, try more, maybe different fine-tuned models for code generation that they're already fine-tuned there. If you go to Hugging Face, there are different models for code generation. Okay.
That's what our impression was like 3 months ago. I don't know, maybe something changed. It was going through for the last 6 months. And the other question, is it, can we use small models for large systems?
Yes,
Yes.
you can use them in rack system.
Small model like the range of 7 million parameters. You get cloud models.
Usually they're faster. So that's what I was trying to say earlier. If you want to use some small model or even any model, I think the best way to decide if you want to use it or not is try it out for the specific task that you have in mind. And if it works good for your task, then I think it's fine, right? Even if it's 1 billion parameter, if it does the right thing for your task, then you should stick with it.
Doesn't do it. The level that we think it was the way. Maybe it was fast, but we were happy, I would say, around 70%.
Okay.
Because we have a local knowledge base. We tried different tracking mechanisms, various techniques, but still we are not very satisfied
Okay.
with the local, with small local.
Yeah.
Accommodate on ourselves. And I was wondering, do we really need cloud models to access for the system performing for the systems?
I mean, if you don't really care about,
My question is, are the open source model, the small open source model,
yeah,
efficient for rack system? But in our experience, they still do not perform well.
yeah. I mean, you need to try them out. Right? Yeah, I think the honest answer is, yeah. But as I said, you shouldn't hang up too much on a specific model, because in probably 12 months, you might need to change it. Even, yes, I think, yeah, and have a framework in place that you sort of can evaluate them for the task that you want.